Welcome to lecture 57. So, this is the last week, week 12, and in this week we are talking about software tools for optimization. We have talked about MATLAB in some length. You are now familiar with various MATLAB functions available in the MATLAB optimization toolbox, and we have seen their use to solve various optimization problems. In our previous lecture, in this week, we have seen that Microsoft Excel solver can be used as an optimizer. It is a built-in optimizer in the Excel spreadsheet. So, in today's lecture, we will take certain examples of constant optimization and unconstant optimization and solve using Microsoft Excel solver tool. So, as a first example, we will take a single variable unconstant optimization problem. This is the problem we have introduced in our previous lecture, that you have to design an open storage tank made of stainless steel with a square base. The volume of the tank will be exactly 50 meter cube. We have to find the dimension of the tank that will require least amount of material. Note that least amount of material corresponds to minimum cost of construction. So, if we consider x as length of side of base and y as height of tank, the total surface area of the tank can be computed as x square plus 4 x y, where x square is the surface area for the base and 4 x y are the surface area for 4 side walls. The volume is given as exactly 50 meter cube. So, x square y is 50, and that allows us to express y in terms of x. So, y equal to 50 by x square. By putting this into expression of a, I get an expression of a as a function of x alone, and a equal to x square plus 200 by x is that relationship. So, this is my objective function. I have to minimize a equal to x square plus 200 by x. So, the unconstant optimization problem formulation is minimize x square plus 200 by x by finding out x. So, for what value of x, x square plus 200 by x will be minimum. That will be the length of the base, length of the side of the base, which is a square, and height then can be obtained from y equal to 50 by x square relationship. So, it is always a good idea for particularly single variable unconstant optimization problem to plot the function and get an idea about the location of the minimum. So, using Excel, you can plot x versus area for various values of x, compute area using this formula and plot f x versus x. You can see that a minimum lies somewhere in the region say 3 to 5 or even between around 4. As we have discussed in our previous lecture, all the calculations in the spreadsheet are done with cell references. We must set up cell entries for the variable and the function we are optimizing. In Excel, the cell containing the formula for the optimizing function is referred to as the target cell. The cells containing the variables are called the changing cells. So, there are two types of cells, target cell and changing cells. The target cells contain objective function and the changing cell contains the variables. So, now let us demonstrate the use of the solver to solve the unconstant optimization problem. Minimize A equal to 200 plus x square plus 200 by x. So, let me launch Excel 2013. So, Excel 2013 is present in this computer. So, let me first zoom it. Okay. So, as we said that it is always a good idea to plot the function, single variable unconstant function. So, let me plot x versus area. So, let me plot for x equal to say 1 to 9. Let us say plot for 1 to 9 and x square plus 200 by x. So, it will be a 2 square plus 200 by a 2. So, you can expand the width of the B cell as required. So, now so you just compute f x, which is x square plus 200 by x for all values of x. Now, you can plot this. Right. So, you can see that the solution or the minimum will lie somewhere around 4. Okay. So, now let us solve the unconstant optimization problem. So, let us give a label called variable. I have one variable x. So, I put x here. In column B, let me give and some arbitrary value of x, which will be used as initial guess by the solver. So, let me skip one row and then write objective function. So, my objective function is minimize area. So, in the same row and under column B, let us write the formula for the area, that is x square plus 200 by x. So, x square will mean B 2 square plus 200 by x. So, now we have defined the problems in Excel sheet. Now, you are ready to solve the problem using solver. So, as we discussed in our previous lecture that the solver is available under data tab. So, click on the data. So, solver is available here. So, if solver is not available there, then you have to click on the file, then you click on the options, click on the add-ins, and you have to select the Excel add-ins. Click on the go to, check the solver add-in box, click OK. So, then you will see that the solver appears under data tab. So, I already have loaded here. If it is not loaded on your PC, you can load the solver just as we demonstrated. So, now click on the solver. So, you get the dialog box for input of solver parameters. Your objective function is this. Set objective. So, here click on this cell and then click on B5, which contains the objective, which contains objective function. So, you see under set objective B5 has appeared. Next, you have 2 and you have options like max, mean, value of. So, we are solving a minimization problem. So, let us click on min. By changing variable cells. So, we are changing x here. So, click on this by changing variable cell and then click on B2, which contains the variable. We do not have any constant here. If you have constant, you can select add and then can add constants and the constants will appear here. Now, you can check make unconstant variables non-negative. That means, the dimensions cannot be negative. So, I should check it. So, it has been checked. Now, look at this drop down menu. You have 3 options: GRG nonlinear, simplex LP and evolutionary. GRG nonlinear is an optimizer which uses generalized reduced gradient algorithm. Simplex LP is for solution of linear programming problems. Evolutionary method can also solve say nonlinear optimization problem. You have options button, you can click on the options and you get this window. So, you have options for all methods, GRG nonlinear and evolutionary. Forward scheme is being used for derivative computation. Let all these things be left to default setting. So, now you are ready to solve the problem, hit the solve button. The solver results is shown in this dialog box. It is written here, solver found a solution, all constraints and optimality conditions are satisfied. Click the radio button, keep solver solution, also select answer under reports. Click on OK button. Now, you look at under column B, it contains the optimal solution for the problem. X equal to 6.4 is the optimal length of the side of the base and the minimum area is 64.63. Once you have x, y can be found out as y equal to 50 by x square. So, this is how you can easily solve using Excel solver any unconstant optimization problem. Now, you will see that answer report is available. Click on the answer report and this contains information about the solution. We started with x equal to 1 as initial guess and then converge to the final solution 4.64. Corresponding to initial guess value of x equal to 1, the area value was 201, that is obvious, x square plus 200 by x. So, 1 plus 200 equal to 201 and the final value is 64.6. The solver was GRG nonlinear, solution time 0.016 seconds, 4 iterations were required. So, there are various informations about the solution procedure under answer reports. So, this is how you can use Excel solver for solution of unconstant optimization problem. So, this was the solution. Now, the next problem is multivariable unconstant optimization problem. So, you have a problem where you wish to minimize x square plus 2y square plus 2z square plus 2xy plus 2yz. The initial guess is 111. The true solution for this problem is 000. So, let us go and solve this problem. So, the problem is x square plus 2y square plus 2z square plus 2xy plus 2yz. You have to minimize this. For that, you have to find out x, y and z. So, let me again launch Excel and I will again zoom it. So, I write variables, give the label, you can put now x, y, z as 3 variables, and then you give objective function, let me expand it, and objective function is minimize f, which is a function of x, y and z. So, let me give case values 1, 1, 1. So, we have to now write the objective function. So, the objective function is x square means b 2 square plus 2 y square, that means b 3 2 into b 3 square plus 2 z square, that means 2 b 4 square plus 2 x y 2 into b 2 into b 3 plus 2 y z, that means 2 b 3 into b 4. So, now press enter. We have now set up the problem in Excel. We are ready to solve. Click on Data tab, click on the solver. So, set objective, click on the set objective cell, click on B6, which contains objective function. We are minimizing, click on minimization. By changing variable cells, we are now changing x, y and z. So, we have to set B 2, B 3 and B 4. So, to do that, click on this. By changing variable cells, you can click on this red button and then drag the cells which contains x, y and z. Click on the red button and you see B 2 to B 4 appears. Check make unconstant variables non-negative, select GRG nonlinear, there is no constant. If there is constant, you have to click on add and then you will be able to add constants. Now, hit the solve button. So, the solver found a solution, all constraints and optimality conditions are satisfied. Click on the radio button, keep solver solution, also click on answer under reports. Now, click OK. So, this is the solution you get. As we discussed initially, the true solution is x equal to 0, y equal to 0, z equal to 0. We obtain the same solution. The objective function value is also 0. Click on the answer report, you get more information about the solution procedure, how much time it took, 4 iterations were required, original function value was 9 and original initial guess was x equal to 1, y equal to 1, z equal to 1, and finally we converge to true solution x equal to 0, y equal to 0 and z equal to 0. Corresponding minimum function value is also 0. So, this is how you can solve a multivariable unconstant optimization problem using Excel solver. So, now again let us go back to our slides. Now, let us consider a nonlinear constraint optimization problem. We used to construct a closed storage tank, width is x, depth is y and height equal to z with exactly 2700 meter square metal sheet. So, this time we used to construct a closed storage tank. The width equal to x, depth equal to y and height equal to z with exactly 2700 meter square of metal sheet. The width of the tank should be double of its depth, that means x equal to 2y. What will be the dimension of the tank so that its volume is maximum? So, we want to problem formulation will be maximize V equal to x into y into z, that is the volume, subject to total surface area should be 2700 meter square. So, 2xy plus 2yz plus 2zx equal to 2700 and another constant is x equal to 2y. So, this is the problem now we want to solve. V equal to x y z subject to 2xy plus 2yz plus 2zx equal to 2700, another constant x equal to 2y. So, we have two constraints. So, now let us see how we will solve using Microsoft Excel. Again let us launch let me expand and then let me zoom so that you can see clearly. So, I write variables I have 3 variables now x, y and z. Let me give their initial value 1, 1 and 1. Then we write objective function which is maximize volume. Let me write the formula for that is x into y into z. That means, B 2 into B 3 into B 4, B 2 into B 3 into B 4. Now, let me skip one cell and write constraint. So, let me write constraint 1 or let me first write constraints and then below it I write constraint 1 and here I write constraint 2. So, what is my constraint? The first constraint is 2xy plus 2xz plus 2zx equal to 2700. So, let me write the formula for that. 2 into xy, that means B2 into B3 plus 2yz, 2 into B3 into B4 plus 2zx, that means 2 into B4 into B2. So, this equals 2700. Constant 2 says x equal to 2y. So, x is B2 equals 2y. So, 2, so equal to 2 into B3. So, we are now done with the problem setting. We are now ready to solve. Hit tab, click on the solver. Set objective. Objective is available under B6, click on B6. We are maximizing the volume. So, click on max button. By changing cells x, y and z, click the red button under by changing variable cells, click the red button and then drag x, y, z. So, B2 to B4 appears. Now, we have constant here. So, click on add button. So, here you give the cell reference that contains constant 1 this. From here drop down menu you take equal to and then from the other side constant 1 right hand side of the constant 1 which is 2700 which is under D9. So, click that. So, now click on add. Now, do the same thing for the second constant. Click on the cell reference, click on B10 that contains constant 2 under drop down menu, click on the equality sign and then click on the D10 which contains the right hand side constant of the constant 2. So, you add. So, both I have added now cancelled to come out. So, now this is what it looks like. You are ready to solve. Make unconstant variables non-negative, chosen GRG nonlinear. Two constants appears here. So, click on solve. So, solver found a solution, all constants and optimality conditions are satisfied. Keep the solver option, also click on answer under reports, click on OK. So, this is the solution. 29.99 means 30, 14.99 means 15. So, 30 x equal to 30, y equal to 15 and z equal to 20. That should be the optimal dimensions giving the maximum volume of 9000 meter cube. Look at here, the constants are satisfied 2700 equal to 2700, 29.999 that means 30 equals 30. So, we have been able successfully to solve the problem. Click on the answer reports to know more about the solution procedure. 6 iterations were required. initial guess values was x equal to y equal to 1, z equal to 1, and we converge to the final optimal solution x equal to 30, y equal to 15 and z equal to 20, leading to the optimal or the maximum value for the volume as 9000 meter cube. So, this is how you can solve constraint nonlinear optimization problem. So, with this we will stop our lecture 57 here.